This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. Lecture 4, Extended Phase Graphs, is broken down into 3 mini-lectures. Lecture-04C covers examples using extended phase graphs. The learning objectives for this lecture are to describe how a spin echo forms using extended phase graphs, to explain and draw phase coherence diagrams, to describe how a stimulated echo forms using EPG, to understand how to use Matlab or Python representations of EPG. So to review the phase graph states, we have this flowchart. We have a state matrix that looks something like this. And reminder that the RF mixes magnetization between states of a given order, that is, between states that have the same subscript. Gradients will shift the transverse states, either clockwise or counterclockwise, depending on whether the gradient is positive or negative. And remember, a unit gradient shifts just one order. Relaxation will apply T2 decay to the transverse states, T1 decay to all of the longitudinal states, and T1 recovery to only the Z sub 0 state. Although not discussed much here, diffusion will apply increasing attenuation with increasing order of the states. So let's go right to our examples. Here we're going to look at an ideal spin echo train. We have a 90-degree excitation followed by 180-degree refocusing pulses. The question here is, which of these EPG basis functions or states will we need to represent the spins with ideal 180-degree pulses? And a reminder that a refocusing pulse about the mx axis will have the rotation matrix shown here. So let's look at this example to find out the answer here. So we start here, and note that we've chosen our T1 and T2 so that E1 and E2, the relaxation attenuation terms, are 0.95 and 0.90 respectively over TE over 2. Remember, this is a spin echo sequence, so the spacing between the 90-degree pulse and the first 180-degree refocusing pulse is TE over 2. So we start in equilibrium, and our MZ is all pointed up to the equilibrium magnetization, and our state matrix has just a 1 in the bottom left corner. We apply a 90-degree excitation, which brings the magnetization along MX. Notice that the F0 and the F plus sub 0 and F minus sub 0 are complex conjugates and are both 1 here. If we move towards the 180-degree pulse, we have two effects. We have relaxation, which has caused attenuation but some recovery of the Z0 state. We also have a twist due to the gradient, and we've approximated this as if this gradient is continuous, but not really, because we're only looking at the magnetization after this gradient. So we play our refocusing pulse, and the refocusing pulse has the effect of inverting the longitudinal magnetization and swapping the F plus sub 1 and the F minus sub 1 states. So we simply move this, and this reverses the direction of the twist. The magnetization then refocuses through another gradient and over time to a spin echo with additional relaxation. So the attenuation now goes from 0.90 to 0.81, which is simply 0.90 squared. Notice that the longitudinal magnetization approximately recovers to 0 over this time. If we continue, we have dephasing by the next gradient, and we have continued relaxation. We refocus, which again swaps the F plus sub 1 and F minus sub 1 states and inverts the longitudinal states. And we refocus again to a spin echo. And given these parameters, the spin echo amplitude is about 0.66. So what we see here is that we've only needed about 4 states here. We've needed Z0 at the very beginning, and we've used Z0, although it's never contributed to signal. But primarily we've used F0, F plus sub 1, and F minus sub 1 to represent everything we need to here. Now let's introduce the concept of a coherence pathway diagram. This is a diagram, a timing diagram, where we plot as a function of time, we basically plot the states that exist that have non-zero values. So if we start at the 90-degree excitation, immediately following this upward ramp shows the transition from an F0 state to F plus sub 1, which is a 1 dephase state. The 180-degree pulse flips this into F minus 1, as shown. It is then refocused again to F plus sub 0 at the spin echo, which is shown by a red dot. It continues to dephase and is refocused again and then rephases to the second spin echo, dephases again, and so on. So this is a very simple coherence pathway diagram because with the ideal spin echo sequence, the spins are very well behaved. You notice that we've included Z0 states. These arise from small amounts of relaxation, of longitudinal relaxation. They don't contribute much to the signal though. So because we have perfect 180-degree pulses, we keep the spins in low-order states. So this is our first example of a coherence pathway diagram. Again, it shows which states can have magnetization, and it can essentially show the pathways that can generate signal, which we'll see later. So to summarize this example, with spin echoes and ideal 180-degree pulses, we never reach a higher order than n equals 1. The coefficients during the gradient, you'll see this animation we're about to play. During a gradient, during dephasing, the coefficients are not really defined because we don't have an integer number of cycles across the voxel. Remember, relaxation results in transverse signal decay. Z0 has some relaxation, so some recovery, and this keeps flipping and doesn't really generate any signal. Z1 only has signal during the 180-degree pulses, but goes back to 0 after each 180-degree pulse. And the final point is very important. The observed signal is always the F plus 0 state. And the reason for this is the other states integrate to 0. So there's never any signal resulting from magnetization in those states, although it can be refocused, as we will see. So let's play this video of the example that we just saw. It will pause at each point where the states are defined, and hopefully give you some intuition for how the magnetization moves through these states. So we excite the signal, it dephases and moves to the F1 state, it is refocused and forms a spin echo, and then this repeats, refocusing, rephasing to a spin echo. And you notice that the amplitude of the state at the end is 0.66. It still says F1 in this video because it just moved from F1, but this is really the refocused state, F plus sub 0. And you notice that the amplitude is the same as from the example that we just showed. And we can look at code for this in the Matlab directory. So let's look at another example. This is a non-180-degree spin echo. So we will see lots of these later in the course. Remember that the ideal spin echo train gives you quite simple RF rotations. However, if we look at the 130-degree rotation matrix, you see that it's not nearly as simple. There are no zeros in this matrix, which means there's substantial mixing between different states. So what results is that if you have an F plus sub n state, it will actually remain. So not all of the magnetization will be refocused. This generates higher order states, and there will be many more coherence pathways that we will see in the coherence pathway diagram. So if we look at the coherence pathway diagram, this is a very nice example of why these are useful. So what you can see is what we sometimes call the primary echo pathway, where the magnetization starts at 0, it goes into the F plus 1 state, it is refocused to F minus sub 1, and it refocuses to a spin echo. It defocuses again to F plus sub 1, is refocused to f minus 1 and forms a spin echo again. That's the primary spin echo pathway. But what you notice is that there are multiple other pathways here. And in fact, some of these can also lead to magnetization at a spin echo. For example, the magnetization, if you follow this pathway, can start at 0. It can go to f plus sub 1. That refocusing pulse can now make it a z1. It can stay in z1 until the next refocusing pulse, which can make it f minus 1, and then it refocuses to a spin echo. So this is actually a stimulated echo pathway. There are also mixed pathways. You can see that you can go f plus sub 1, f plus sub 2, f plus sub 3, refocus to f minus sub 3, f minus sub 2, f minus sub 1, and refocus at the third spin echo. So this is a pure spin echo pathway. And this is the case where the magnetization has essentially passed through the first and last of the refocusing pulses. So lots of interesting things about this diagram. Another point is only the F0 state produces a signal, so all of the other states are dephased, and if you follow the dashed line pathways, you see that those pathways never lead to a signal. And this is very important, as we'll see when we talk later in later lectures about spin echo sequences. So it's a bit of a complicated diagram, but what this shows you is the possible states that can exist at any time. So let's look at an animation of this example here. We're not going to show all the states that build up, but we show at least the second state here. But as we just saw, the magnetization does build up in higher order states, but this does not really contribute that much to the spin echo. Again, we'll study this at length during the spin echo portion of the course. So let's animate this, this sequence. So we have excitation, dephasing, refocusing. Notice we still have signal in the transverse states, but we still have quite a good spin echo forming. Now it plays quite quickly, but you also notice that magnetization is actually coming back from the higher order states, if you watch that clip. So maybe if I slow it down for a second here, we can go through this more slowly. So the magnetization is excited, dephases, and after that first refocusing pulse, you still have some twist in the f plus sub 1, and you also have generated some Z1 magnetization. Now, here, that F1 magnetization will become an F2. We form a spin echo. This will continue to dephase to F3, where it goes off the screen, but that magnetization will come back after the next refocusing pulse. But notice during this refocusing pulse that there's some of the Z1 state will now contribute to F1. And this actually changes the contrast in the sequence, and we'll see this much more later on. So what you see is by changing the pulses from 180 degree pulses to 130 degree pulses, that the dynamics have become much more complicated. And now you see some F minus sub 2 magnetization coming in. And it's very small, but this magnetization can get refocused. Now let's look at another example. This is a combination of a stimulated echo and a spin echo, and this is a bit of a mystery on what these terms mean. So I'm going to state that a spin echo is when the magnetization remains transverse, but is refocused. And a stimulated echo is when the magnetization passes through a longitudinal state. So we excite with a 90-degree pulse. We're going to play unit gradients that are shown here, and we're going to track this using a Matlab function EPG_show. And right after the excitation, we only have the F plus state. Now this is a great example of don't worry about the phase of the magnetization. Here it's along minus my, but this really doesn't matter for this example. In fact, you would generate a stimulated echo regardless of the phases here, although the amplitude might change. Okay, so we go through the first gradient, and of course this results in dephasing of that signal, and we can see the 3D view. We have a dephased disk. Now we're going to play a 90-degree pulse again about mx, and notice that that pulse has split the magnetization into f plus sub 1, f minus sub 1, and z1. And in the 3D view it's a bit hard to see, but you actually have a disk that's up on its side now. We play a unit gradient, and what's going to happen here? Well, we've actually refocused, so the Well, first let's start with F plus sub 1 has gone to F plus sub 2. So that magnetization is further dephased. The F minus sub 1 magnetization has refocused to form a spin echo. And if you look at that series of pulses, even though it doesn't have a 180-degree pulse, we've generated a spin echo from that 90-degree pulse. And notice, of course, that the gradient has not affected the longitudinal state Z1. So we've managed to basically split our magnetization now into different orders here by this simple combination of pulses. We play another gradient, and what happens is the spin echo now dephases. The F plus sub 2 magnetization dephases further, and again the Z1 is unchanged. So we'll play one more gradient pulse, and of course things shift to the right again. And again Z1 is unchanged. Now we've shifted out all of the transverse magnetization. We're only left with magnetization in Z1 in the lower order states here. So we play another RF pulse here. And this pulse has the effect of taking that Z1 magnetization and mixing it between F plus sub 1 and F minus sub 1. Notice that a 90-degree pulse leaves nothing here in this case. Now we have magnetization in F minus sub 1, we play another gradient, and that will refocus to what's called a stimulated echo. So I hope this example gives you some intuition about the difference between spin echoes and stimulated echoes, but be patient if it isn't totally clear yet. You can see the example Matlab code in the file Lec4 example 5 in the Matlab folder. So let's look at another example, again a stimulated echo sequence. So we're going to follow the sequence through time, and we'll just look again at which states are populated at each point here. The point here is now the flip angle is not a 90-degree angle, it's a 60-degree angle. What we see here is we start with longitudinal magnetization. After the 60-degree pulse, the transverse spins are still aligned in an F plus 0 state, but we still have some residual longitudinal magnetization here. After the first gradient, we've now gone from everything being fully in phase to an F plus sub 1 state, but of course we still have some longitudinal magnetization here, and these are unaffected by the gradient. We play another RF pulse, and what this does is it again splits the longitudinal magnetization into an F plus sub 0, or excited magnetization, and some residual longitudinal magnetization. The F plus sub 1 magnetization is split into F plus 1, F minus sub 1, and Z1 states, as we've seen before. So already after 2 RF pulses and a gradient, now we have magnetization in 5 different states here. We can play another gradient cycle here, and we can see that this gets even more complicated here. So the F minus 1 state is of course refocused, and we can call this F minus sub 0 or F plus sub 0. The F plus sub 0 magnetization and F plus sub 1 move to F plus sub 1 and F plus sub 2. The Z0 states are all unaffected, and this process continues. So we will generate higher and higher order states here, but we will have refocusing. And this refocusing takes the form of a combination of spin echoes and stimulated echoes. And a subtle point is, unlike the previous example, the spin echoes and stimulated echoes will actually be mixed here. They're not split off like we saw before. Sometimes the spin echoes and stimulated echoes will add in phase, and sometimes they'll be opposed phase, which we'll see later on. Okay, so we'll show one more example in this lecture. This is just looking at the coherence pathway diagram for the stimulated echo sequence. What you see is it looks quite similar to the spin echo coherence pathway diagram when we used 130-degree refocusing pulses, except that here we only have one gradient between the RF pulses. So the magnetization starts in phase, moves into an F1 state, is split into 3 different states. It can continue to dephase if it's in the F0 or the F2 state here. Sorry, this F plus sub 0 is generated by excitation, This is a refocusing pathway, so you can clearly see a spin echo pathway, and you can actually see a stimulated echo pathway here too, where the magnetization goes from F0 to F1, then moves to Z1, then moves to F-1 and refocuses. So at the end, that one would refocus at the end. Okay, so just again looking at the different states that can be populated at any given time in the sequence. So now we'll talk briefly about Matlab Formulations, which we'll work much more with in class. The extended phase graph simulations can be very easily built up using modular functions, and these are in the class GitHub. And really with about 5 functions, you can create almost all of the examples that I've shown. We have simple transition functions. EPG RF simply applies an RF pulse to the Q matrix. EPG grad applies a gradient. EPG G relax is a compact way to apply gradient, relaxation, and diffusion all at once. And then there are the transformations to and from the magnetization domain. So we can transform, basically the magnetization domain here is called spins, so we can do EPG spins to FZ and EPG FZ to spins. So these will give you some intuition about the transformation if you actually look at these functions. So here's just an example using this code. We've already seen the stimulated example echo sequence. So what if we want to quantitatively simulate what happens here? You see that the MATLAB code here is just 7 lines, which is really nice. And here we're trying to calculate the signal at the end of this sequence here. So basically we start with equilibrium magnetization, and then we go through a loop through the different flip angles here. We apply an RF, and then we apply gradient and relaxation, and we're done. And then notice at the end that the signal is the top left element of the Q matrix here. So this is very nice. If we want to simulate this type of a sequence, we've done it in 7 lines of code. And I would argue that doing this directly using material before this lecture would take quite a bit more effort. So if we do this, we can actually use the fplot function in MATLAB, which is a really compact way to look at the signal. And stimulated echo sequences are actually used because they're quite sensitive to the flip angle, so they can be used to actually calibrate the flip angle or measure the flip angle in some cases here. So what you can do is you can very quickly plot the signal versus flip angle for 3 TRs of this sequence. Okay, a final point, although we're not going to spend much time on it, it's very important to note that diffusion weighting can easily be applied using the EPG formalism. In fact, there are ways to apply magnetization transfer that have been recently developed as well. The details for diffusion are shown in this paper here, and in fact you can derive a multidimensional extended phase graph with multidimensional diffusion. When you apply this in one dimension, it's simply seen that the attenuation is greater with increasing n for both the transverse and longitudinal states. You do have to calculate a physical k number in real units in order to apply diffusion, and that's simply because the diffusivity d is a physical number. And then how you apply this differs slightly. If you're playing a gradient, you actually have an additional delta k over 2 and delta k squared over 12 term in this equation. So this is quite workable, and the power of this is that you can easily calculate the diffusion sensitivity of different sequences as well as different parts of the sequence. So it's very much worth mentioning. Okay, this brings us to our summary for this lecture. The 90 and 180 degree RF pulses tend to swap magnetization between states, so these rotation matrices can have zeros in them. We generally see RF pulses mixing states of order n, but remember the RF pulse cannot create twists or create cycles in the longitudinal magnetization. The gradient pulses will transition from F plus sub n to F plus n plus p, and from F plus sub n to F plus sub n minus p, depending on if this is a positive or negative pulse, in this case, the area can be, instead of unit area, it can be p times the unit area. So you could have a gradient that dephases more than one cycle. So it would dephase p cycles here. And you can have positive and negative gradients. We've shown coherence diagrams, and these show the progression through different transverse and longitudinal states and show how echo pathways can form. Notice that these typically are not quantitative, but just show the presence of non-zero states. We can use signal calculations, which will actually quantify the population of each state, and these will give very accurate simulations of many spins inside a voxel, again assuming that you're using unit gradients that dephase an integer number of cycles. And finally, we've introduced some of the functions in Matlab that we will work through much more in class and on homework. The most important of these two pulses are EPG-G relax, which does gradients and relaxation, and EPG-RF, which simulates RF pulses. And these two functions can be used to simulate a lot of common pulse sequences just by themselves. And then there are many other functions on the class GitHub that start with EPG underscore that can be explored. So now that we've built up the EPGs and we'll practice using the EPG formalism, we'll see later on in other lectures how EPGs are used for common sequence calculations.